Very good afternoon, students.
Good
Afternoon,
afternoon,
sir.
sir.
Good afternoon, sir.
Good afternoon. So let us start the discussion without wasting any time. Last class we have discussed about emulsions and all, and then we have to study about colloids around us, and then we have to proceed with the applications of colloids, right? So if you try to think of colloids around us, blue color of the sky, dust particles along with water suspended in air scatter blue light, which reduces our reaches our eyes, and the sky looks blue. Why the sky is looking blue? Because the dust particles along with water which are suspended in the air, they will be forming the colloidal size, and colloidal particles can scatter the light, and that scattered lights, whatever it is reaching us, that will be appearing blue. So blue color of light, blue color of sky is just due to scattering of light by the colloidal particles. Fog, mist and rain. When large mass of air containing dust particles is cooled below its dew point, what happens? The moisture from the air condenses on the surface of these particles. Whatever the water we have, that is going to be condensing on these particles, and they will form a fine droplet, which will be nothing but a colloidal particle. These particles on which the moisture has been condensed, they will be in the colloidal size, and they are called as fog or mist. Clouds are aerosols of small droplets of water in air. What are clouds? Clouds are aerosols of a small droplets of water in air, and it is also possible to cause an artificial rain by throwing electrified sand or oppositely charged salt. So on the cloud, whatever the charge we have, if we try to throw oppositely charged salt, mutual coagulation occur, and because of that mutual coagulation, they will not be present in that uh, colloidal form. Rather, they will form the coagulate, and the rain will occur. So artificial rain can be caused by throwing electrified sand or oppositely charged salt. Thereby, you can decrease the charge and thereby making the coagulation possible. Food articles, milk, butter, ice cream, etc. All these are colloidal particles. So around us, we have a lot of colloids. That's what we mean to say. Around us, we will be having a lot of colloids. Blood, it is also a colloidal solution of aluminate substance. The stypic action of alum and the ferric chloride solution, that is actually causing the coagulation of blood, which is forming a clot. So whenever we have any clot, whenever we have any cut or something, immediately sooner the clot is going to be formed. So the stypic action of alum with the ferric chloride, that will cause the clot formation. The clot, whatever it is going to be formed, that will stop the further bleeding. Okay. So the blood is actually a colloidal solution of albuminate substance, where the stypic action of alum and ferric chloride, that is going to be forming the clot, which will stop further bleeding. Soils, fertile soils are colloidal in nature, in which humus acts as a productive colloid. Soils, they are also colloidal solutions. And formation of delta, you can see river water is a colloidal solution of clay. In river water, we have colloidal solution of clay, that is the clay particles are in the colloidal size. Sea water contains a large number of electrolytes. When river water meets the sea water, what happens? The electrolytes present in the sea water coagulate the colloidal solution of clay, resulting in the deposition with the formation of delta. So you can have a lot of clay is going to be deposited. Why? Whenever the river water reaches the sea water, in the river water, whatever the colloidal solution of clay we have, it will have a specific charge. In the sea water, we have a lot of electrolytes. Those electrolytes, whenever they are mixed with the salt, what happens? The mutual coagulation occurs, or you can say charge neutralization occurs. Charge neutralization occurs, and thereby, because of charge neutralization, you will have the formation of delta. Is that clear or not?
Yes, sir.
Yes, sir.
Yes. So these are some of the colloids which we'll be seeing around us, or colloids around us. Applications of colloids, if you go with this idea, electrical precipitation of smoke, Purification of drinking water, medicines, and tanning. All these are the applications of colloids. If you think of a smoke, electrical precipitation of smoke, the smoke, whatever it is produced in the industries, that is not directly released out into the atmosphere. Rather, whatever the colloidal particles we have, they are actually stopped by passing them to some chimney. By passing them to some precipitator, we will remove the colloidal particles. Like in the precipitator, what happens? We have many plates. Like smoke is obtained from the industry, that is passed now. In the smoke, we have a lot of particles. Those particles, upon reaching the respective oppositely charged plates, they will coagulate and they will fall down. Whereas the other gases, which are not colloidal gases, they will be moving out again through the chimney. So we have electrical precipitation of smoke. So this was the scenario. So where we have smoke passing through and the colloidal particles will be sticking to the plates, and all those will form a coagulate because the charge has been neutralized for those particles and only air has been passed. Smoke is a colloidal solution of solid particles such as carbon, arsenic compounds, dust, etc. in air. The smoke, before it comes out from the chimney, is led through a chamber containing plates having a charge opposite to that of carried by the smoke particles. Whatever the smoke particles we have, they will have a specific charge because colloidal particles will have charge. Opposite to that charge, we will have the electrical plates or plates. These plates which are oppositely charged, they attract the colloidal particles, and upon attraction, the colloidal particles loses their charge and ultimately they will be falling down. The particles on coming in contact with these plates lose their charge and they get precipitated or coagulated. The particles thus settle down on the floor of the chamber, and the precipitator used here is said to be quartal precipitator. The precipitator, whatever you are using here, that is said to be quartal precipitator. Is that clear or not?
Yes, sir.
Purification of drinking water. The impurities obtained from natural sources often contain suspended impurities. Like the water, whatever you get from the natural sources, it will contain impurities. Alum is added to such water to coagulate the suspended impurities. Like this is a pure water, but generally we have impure water, which is obtained from natural source. That impure water, to that if you try to add alum we have a lot of electrolytes like potash alum, 2K plus, 2Al plus 3, 4 sulfate. So whatever the particles we have, whatever the colloidal particles we have, they all will be coagulated because of the addition of alum. So like that, whatever the precipitate we form, that can be removed by filtration. Yes or no? Alum is added to such water to coagulate the suspended impurities and make water fit for drinking purpose. Like that, you can actually do the purification of drinking water with respect to this coagulate formation. Medicines. Most of the medicines are colloidal in nature. Most of the medicines are colloidal in nature. Many medicines are there. What are the some of the examples of such medicines? We will be listing it down. Like all these medicines: Argerol, colloidal antimony, colloidal gold, milk of magnesia. Argerol is a silver salt used as an eye lotion. That is again a colloidal solution. Colloidal antimony is used for curing Kala-azar. Colloidal gold, that is used for intramuscular injection. Milk of magnesia, an emulsion, that is used for stomach disorders. So all these are medicines. In the medicinal usage also we have a lot of colloidal systems. So colloids are more effective. Why? Because they also have large surface area and they can be easily assimilated. Because of large surface area, the absorption of the respective viral particle or bacteria on these colloidal particles or drug particles becomes easier. Yes or no? Because of that more surface area, its rate of reaction will also be greater. So they also have a lot of application in the medicinal industry. Tanning. Tanning means what? Animal hides are colloidal in nature. Animal hides are colloidal nature. When a hide means skin. When a hide which has positively charged particles is soaked in tannin, which contain negatively charged colloidal particle, what happens? Mutual coagulation occurs. Because animal hide, which is positively charged particle, is soaked in tannin, which is negatively charged. So mutual coagulation occurs. Because of that mutual coagulation, what happens? The hardening of the leather will be taking place. The positively charged animal hide, upon soaking in tannin, tannin is a negatively charged colloidal particle. So that mutual coagulation will happen and the hardening of leather will take place. And this whole process is also called as tanning. And we nowadays are using chromium salts in the place of tannin. So different other chemicals like sodium salts or chromium salts were used in the place of tannin. Same thing happens to normal skin also. Our skin will have a particular charge, and whenever oppositely charged particles are falling on our skin also becomes hard. Yes or no? That is nothing but tanning. Is everything clear so far? So these are the applications of colloidal particles. Like as of now, we have seen applications of colloidal particles as well as colloids around us, as well as colloids around us. Then comes the next, the third important concept of surface chemistry. In surface chemistry, we have 3 points to discuss. One is absorption, concepts of absorption. Next one is respect to colloidal systems, and then we have catalyst and catalysis. So we'll study about catalyst and catalysis now. Catalyst and catalysis, like this is also a very important part. What are catalysts? Catalyst is a substance which will actually increase the rate of reaction. Substance which can actually accelerate the rate of chemical reaction, they are said to be catalysts. How they can increase the rate of reaction?
By
By
decreasing the
decreasing
activation energy.
activation energy.
By decreasing the activation energy. With increase in temperature, the rate of reaction will also increase, but it will affect the activation energy or it will not affect?
Not
will not
affect, sir.
It will not affect, right? We have studied the same in chemical kinetics as well. Substance which accelerate the rate of chemical reaction and themselves chemically and quantitatively unchanged after the reaction is done, that is known as catalyst, and the phenomena whole process is to be catalysis. The whole scenario is said to be catalysis. So if you can try to plot a graph, we have somewhere reactants here. Reactants are going to be converting into products if you talk of exothermic reaction. So now in the presence of catalyst, you will have this scenario. This is the activation energy in the presence of catalyst. This is activation energy in the absence of catalyst. So in the presence of catalyst, the activation energy, the threshold energy will be decreasing, whereby rate of reaction is going to be increasing. Types of catalysis, there are 2 types of catalysis. What are those? Homogeneous catalysis as well as heterogeneous catalysis. So all these points we are going to study. What are the points we will study? Types of catalysis, some of the related terms, general properties, theories of catalysis, catalysts in industries, zeolites and enzymes. So first one, types of catalysis. How many types of catalysis we have? 2 types, homogeneous catalysis and heterogeneous catalysis. Homogeneous catalysis means what? Reactants and catalysts, they are in the same phase. Heterogeneous means reactants and catalysts, they are in different phase, right? So homogeneous catalysis, when the reactants and the catalyst are in the same phase, the catalysis happened is said to be homogeneous catalysis. First one you can take off lead chamber process. So if you consider this particular process, 2SO2 plus O2 gives us to 2SO3. 2SO2 plus O2 gives us to 2SO3. SO2 is a gas, O2 is a gas, SO3 is also a gas. So reactants are these. These are reactants. NO is the catalyst. NO is the catalyst. The reactants and catalysts, they are in the same phase, gaseous phase. So that is why this process of conversion of sulfur dioxide into sulfur trioxide by treatment with oxygen in the presence of NO is a homogeneous catalysis process because reactants and catalysts are in the same phase. Similarly, inversion of cane sugar cane to sucrose plus H2O in the presence of H2SO4, you will form glucose and fructose. Sucrose plus water in the presence of acid, it will form glucose and fructose. Here also what you can say? Here also catalyst is actually H2S4, which is in the aqueous media. Sucrose and water, they are actually respect to reactants, like hydrolysis of sucrose you are doing in the presence of acid media. Reactants and catalysts, they are in the same phase. So that is nothing but again homogeneous catalysis. And in sucrose, what type of linkage we have? Sucrose.
Alpha 1, 4 glycosidic linkage.
Yeah, which carbon? C1 of alpha
C1
D glucose.
D-glucose, C4 of beta D fructose.
C4 or C2?
C2.
C2 of beta D fructose. Okay. C1 of alpha D glucose with C2 of beta D fructose, they are going to be linked to produce respect to sucrose. And that sucrose, whenever you try to do the hydrolysis in the acidic medium, you generate glucose and fructose. This is also homogeneous catalysis because reactants and catalysts, they are in the same phase. Heterogeneous catalysis. Heterogeneous catalysis means when the reactants and catalysts are in a different phase. You can take Haber's process. Yes or no? Decomposition of H2O2. H2O2 aqueous is converting into H2O and O2. This is happening in the presence of catalyst like platinum. H2O2 is in aqueous media, whereas platinum is a solid. So reactant and catalyst they are in different phase. So that is why heterogeneous catalysis. Haber's process. N2 plus 3H2 gives rise to 2NH3. Fe is the catalyst. Iron is the catalyst, iron solid. Molybdenum is the respective promoter. N2 plus 3H2 gives rise to 2NH3. Fe is the respective catalyst. Molybdenum is the respective promoter. And this reaction is nothing but your Haber's process. It is also coming into the category of heterogeneous catalysis. Simple logic. Catalyst and reactant, they should be in different phase. Ostwald's process, ammonia plus O2 gives rise to NO plus 6H2O, which happens in the presence of platinum. 4NH3 plus 5O2 in the presence of platinum forms 4NO and 6H2O. This is again heterogeneous catalysis because platinum is in solid phase, reactants are in gaseous phase. Hydrogenation of vegetable oils plus H2 converts to vanaspati ghee. Yes or no? Which will be happening in the presence of nickel. Again, vegetable oils plus H2, they are nothing but respect to reactants, and a catalyst is in different phase. So again, it is coming into the heterogeneous catalysis. Is that clear, students?
Yes, sir. Yes.
Yes or no? So this is a basic example, homogeneous and heterogeneous catalysis, and different examples have been given in each category. Now some other related terms we can discuss. What are the other terms which you can discuss is promoters, inhibitors, catalytic poisons, autocatalysts, induced catalysts. Promoters, inhibitors, catalytic poisons, autocatalysis, and induced catalysis, these are the different things which you can study. Promoters, what are promoters?
Which promote the reaction.
Like what is catalyst and what is promoter?
Promoters increases the efficiency of catalyst.
Yeah, we use the term activity instead of efficiency. The activity of the catalyst, if it is increasing, then that particular substance is said to be promoter. And how the promoter is going to increase the activity of the catalyst? I have discussed this earlier, if you remember. In organic chemistry itself, we have discussed.
Is just the
Yes, what is that? Promoters can increase the activity of catalyst. By following ways. First one, increasing lattice spacing. What do you mean by that? Like we have a particular metal lattice like this, and we have adsorption happening of a particular gas. H2 is going to be absorbed, let us say. It is stick to this element and this atom and this atom. Now the same thing if you try to do in the presence of promoter, molybdenum is acting as a promoter, right? Now this is iron atom, this is also iron atom. Now the H2 gas which has been absorbed, that is absorbing to the two adjacent iron atoms, interstitial positions are occupied by molybdenum. So because of interstitial positions occupied by molybdenum, the lattice spacing has been increased. Because of increase in lattice spacing, the bond length between the two hydrogen atoms that has been increased. Because of increase in bond length, what happens? The reaction will be happening at a greater rate. That is the first idea. Second idea is it can also increase the peaks of surface, thereby increasing adsorption. It can increase it can also increase peaks on the surface and thereby increasing adsorption. Understand this point carefully. Whenever you have a particular metal, on that metal, whatever the adsorption happened, and if I try to decrease the bond energy, obviously rate of reaction will increase. How the bond energy can be decreased? Because of increased lattice spacing. That means some of the promoter atoms are occupying the interstitial sites in the crystal lattice structure of the metal. Some of the promoter atoms, they were occupying the interstitial sites in the crystal lattice structure of metal, thereby increasing the lattice spacing, thereby the atoms which got adsorbed, their bond length will be increased, thereby decreasing the bond energy. But can I say all the promoter atoms only occupy interstitial sites? Can I say like that?
No.
We cannot say that all the promoter atoms are occupying the interstitial sites. There are many promoter atoms which are not occupying interstitial sites. They can also increase the peaks. Like the surface may be smooth earlier, but now because of the promoter atom, there will be some height and depth, like peaks have been introduced because molybdenum has a different size when compared to iron. Because of the presence of molybdenum atoms, the peaks on the surface of that particular metal will be increased. Because of increase in the peaks, there you will be having greater adsorption. Like that, promoters can actually increase the adsorption, thereby increasing the activity of the catalyst. First point. Second one, inhibitors. Inhibitors means what? Catalysts are those substances which increase the rate of reaction by decreasing activation energy, by decreasing threshold energy. Inhibitors are those substances which decrease the rate of reaction by increasing activation energy, by also increasing the threshold energy. Substances which decrease the rate of reaction are called as inhibitors. Like Na2SO3 plus half O2 gives rise to Na2SO4. C6H5CHO plus half O2 gives rise to C6H5COH. So these are the respective reactions where you will have C2H5OH, diphenylamine, they are acting as the inhibitors. So inhibitors means they will increase the activation energy. So this was the reaction, let us say, and this is how the reaction is going to be there in the presence of inhibitor. Inhibitors increase the activation energy. Inhibitors increase the respective activation energy. Right? Catalytic poison. Substances whose presence decreases or destroys the activity of catalyst. Substances whose presence. Poison means what? Poison means something which will be decreasing the activity of catalyst. Just a second. Yes, substances whose presence decreases or destroys the activity of catalyst. Promoters are those which are increasing the activity of catalyst, but poisons are those which are decreasing the activity of catalyst. How the poisons will decrease the activity of catalyst?
Competitive inhibition.
Competitive inhibition. Yes or no? Poisons can decrease the activity of catalyst as they can act as competitors for reacted molecules. As they can act as competitors for reactant molecules. Autocatalysis. Autocatalysis means what? Autocatalysis means,
Where the reactants catalyzes its reaction itself.
sorry,
Sir, either reactants or product catalyzes the reaction.
yes. When one of the product of the reaction begins to act as catalyst, not the reactants. If the reactants itself are catalyzing, then the rate of reaction will be very, very high in the initial time only. Generally, the formed products, generally one of the formed products, they are going to catalyze the reaction, or they are the source of catalyst. Like in the reaction of esterification, like hydrolysis of ester, the reverse reaction is esterification, but ester, whenever you treat with water, it is nothing but acetic acid and C2H4OH. Generally, if you do this reaction in the organic chemistry, there we have clearly mentioned H2SO4. But here no acid is mentioned. I am just doing the hydrolysis of ester. What happens in the hydrolysis of ester? We have CH3, C double bond O, OC2H5, and we have water which is acting as a nucleophile. The lone pair of electrons are present on oxygen. The lone pair of electron present on oxygen that cannot directly go and attack this electrophilic carbon because electrophilicity is weak. So rate of reaction initially is low. But as soon as the reaction occurs, although the reaction started slowly, but once the products are formed, one of the product is acid, which is again dissociating to produce CH3CO minus and H plus. The acid is providing H plus. Once the H plus is there, what happens? Lone pair of electron present on oxygen, they can pick up this proton, increasing the electrophilicity or not.
Yes.
Now the attack of water is very high. That means initially at time t is equal to 0, where there was no acetic acid, the rate of reaction is low. But as soon as the acetic acid is formed, it provides the H plus ions, so that the ester will react with the H plus, generate a protonated ester. Thereby, the rate of reaction is going to be high. So that means the hydrolysis of ester forming acetic acid and C2H4OH, the acetic acid will be acting as an autocatalyst. The same type of reaction you can think, KMnO4 plus H2C2O4 plus H2SO4 will form MnSO4 plus K2SO4 plus CO2 plus 8H2O. This was the reaction where you can simply observe more like MnSO4, whatever it is going to be produced, that is actually acting as the autocatalyst. That is actually acting as the respective autocatalyst. Is that clear or not?
Yes.
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 If I try to plot a graph between,
First it decreases, then slower, then increases.
yes, concentration of, let us look at the reaction of concentration of ester taking on the y-axis, and I have taken time on the x-axis. So concentration of ester is going to be maximum at time t is equal to 0. So maximum somewhere here. As time proceeds, what happens? The concentration of ester is the reactant, it should decrease. So time t is equal to 0 to 5 seconds. So ester concentration decreased. But as soon as the ester is converting into product acetic acid, the decrease in the concentration will be drastic. Understood this or not? It will decrease, the reactant concentration decreases, but decreases drastically and then saturates. That is how the graph can be drawn. Same type of graph you can draw with concentration of MnO4 minus versus time also. So as the time proceeds, initially the decrease in the concentration is going to be low. As more and more time is proceeding, we have greater decrease in the concentration of ester. Right. So Mn plus 2 is acting as an autocatalyst in the second case, whereas in the first case, acetic acid, which is producing H plus ion, that is acting as an autocatalyst. Induced catalysis. When a chemical reaction enhances the rate of another chemical reaction, it is called as induced catalysis. Like Na2SO3 plus R4 gives us to Na2SO4. That reaction is not going to happen at a greater rate. But whenever you try to take Na3SO3 plus R4, like one of the reaction will induce the rate of the other reaction. Like these two reactions are actually coming under the category of induced catalysis. When one chemical reaction is actually inducing the rate of other chemical reaction, that is said to be induced catalysis. So these are the 5 points: promoters, poisons, inhibitors, autocatalysts, as well as induced catalysts or induced catalysis. Is everything clear, students?
Yes, sir.
Yes, sir.
Yes. General properties you have to think of catalyst. A catalyst remains unchanged in mass and chemical composition, but can change their physical state. A catalyst will remain unchanged in mass. Its mass is not going to be changed and chemical composition will not be changed. Only a very small amount of catalyst is sufficient to catalyze a reaction. Only a very small amount of catalyst that is sufficient to catalyze the reaction. It does not initiate a reaction. The catalyst will not be initiating a chemical reaction. Rather, catalyst will increase the rate of chemical reaction, but do not directly increase the chemical reaction, but it helps in that. When a catalyst is solid, mainly adsorption is going to happen, and because of adsorption, we can think in terms of surface area. Whenever we have a solid catalyst, what you will take? You will take the powdered form of that particular solid catalyst, where you will be having greater adsorption because of increased surface area. It does not initiate a reaction. When a catalyst is solid, it usually is more effective when used in finely divided form, because more surface area will have more surface area will have more adsorption. Generally, catalyst does not change the nature of products. It will not be changing the nature of products. Like whatever the products we have, the same type of products are going to be obtained from the same set of reactants, but only the path has been changed. Each catalyst is generally specific for a given reaction. What do you mean by this? This means even though the reactants are same, but if I just try to change the catalyst, the type of product formed will be changed. This means even though reactants are same, changing the catalyst changes the type of products formed. Okay. For example, if you can think of that category like CO plus H2, CO plus H2, mixture of carbon monoxide and H2 is also called as what? What type of gas?
Synthetic gas.
Synthetic gas or syngas or water gas. So CO plus H2 will be reacting in the presence of nickel catalyst to form CH4 plus H2O. CO is a gas, H2 is also a gas. If I do the same reaction, CO plus H2, but in the presence of other catalyst like ZNO, copper, or ZNO CrO3, Cr2O3, you will form respective CH3OH, which is a methyl alcohol. That means if I try to change the catalyst, what happens? The type of products obtained are changed or not. If I try to change the catalyst, even though the reactants are maintained same, the products obtained are different. So you cannot say as the products are same, even though you change the catalyst, you are getting the same products. That is wrong. Catalysts are highly specific for a given reaction. For a different type of reaction, we need a different types of catalysts. And if you talk of enzymes, enzymes are even more highly specific. Okay, enzymes are also catalyzing the reactions. The enzymes are even more highly specific when compared to normal catalyst used in the reactions. A catalyst does not change the equilibrium state of a reversible reaction, but helps to achieve the equilibrium state or position of equilibrium in lesser time. It does not change the equilibrium time of a reversible reaction. And also catalyst, will that change the free energy change?
No, sir.
Why? Also delta G, delta H, delta U,
Because they are state functions.
delta S are same in the absence of catalyst also. In the absence and presence of catalyst also. As they are state functions. Very good. And in case of a reversible reaction, there will be an establishment of equilibrium. That equilibrium is going to be achieved fastly, that is in the lesser time, but the position of equilibrium is not going to be changed, even though you try to use the respective catalyst. Right. So this is a potential energy and the course of reaction. Reactants will have somewhere energy here. And let us take an exothermic reaction where we have products here. This is an uncatalyzed reaction where we have activation energy A1. And delta H is the energy difference between the reactants as well as products. Whenever you try to catalyze the reaction, in the presence of catalyzed reaction, what happens? The activation energy has been changed. So that is why it is said to be catalyzed reaction. So we are saying the activation energy is going to be decreased in the presence of catalyst, but how it is decreased? That also you need to understand. Yes or no? Until now we have studied that the activation energy in the presence of a catalyzed reaction is going to be decreased. Because of that, more reactants are crossing the energy barrier. Because of that, more products are obtained. But how come the activation energy is going to be decreased? How the activation energy is going to be decreased means we have two scenarios. Their theories of catalysis can be explained. The intermediate compound theory or the adsorption theory will try to explain how the catalyst is going to function. A catalyst changes rate constant of a reaction. A catalyst do not change free energy change delta G. Why? Because delta G, delta H, delta U, delta S, all those are state functions. A catalyst may participate in the mechanism of the reaction. The catalyst first reacts with the reactant molecules to form an intermediate compound. That intermediate compound will have less repulsions, so less energy. That will again convert to the product. Are you understanding this point or not? If the two reactants are reacting, they will form an activated complex which has higher energy. If one of the reactant react with the catalyst to form an intermediate compound, and that intermediate compound can react with other reactant to form a product, then the repulsions are low for that intermediate compound, thereby more product can be formed. Yeah, this is what you can explain in the theories of catalysis. We have two theories, intermediate compound formation theory as well as adsorption theory. First theory is intermediate compound formation theory. What does this theory explain? This theory explains homogeneous catalysis mainly. Intermediate compound formation theory will be explaining the homogeneous catalysis, whereas adsorption theory will be explaining the heterogeneous catalysis. As per this theory, the catalyst combines with one of the reactant to give an intermediate compound. Like we have A plus B gives rise to C in the presence of product. So A plus P will be forming some K. That K will be reacting with B to form C. K is nothing but the intermediate. Understood this point or not? The catalyst will be reacting with some, like you can say, I can change the names. Generally C is used for catalyst, P is used for products. So A plus C, catalyst will react with one of the reactant to form intermediate. That intermediate react with a compound B to form product, and a catalyst is released back. So this theory explains homogeneous catalysis only because the reaction between C and A is happening. So if C is in different phase and A is in different phase, then the reaction between A and C is not going to be happening greatly. That is why homogeneous catalysis will be explained by this theory. This intermediate compound react with the old reactants and gives the product, and that will also regenerate the catalyst in its original form. So catalyst is actually used in the mechanism of reaction, again reproduced back after the final stage. Look at the reaction. Sulfur dioxide react with O2 to form sulfur dioxide. SO2 plus O2 forms 2SO3. If you look at this reaction, first step is NO is a catalyst which will be reacting with oxygen to form NO2, which is an intermediate compound. That NO2 will now react with SO2 to form SO3, and NO is released back or regenerated back. Understood the steps or not? The catalyst is reacting with the reactant to form an intermediate which has less energy than activated complex formed in the absence of catalyst. Whatever the activated complex we form in the absence of catalyst, no. When compared to that, this intermediate will have less energy, thereby it is going to be called as a catalyst. Why it is called as a catalyst? Because here this particular compound has less energy when compared to the activated complex formed in the absence of catalyst. Clear or not?
Yes, sir.
Yes. Adsorption theory. Then comes the next adsorption theory. So we have a particular catalyst. We have hydrogen gas. We have respective alkenes also. Adsorption theory will try to explain how the respective catalyst is, like it is mainly for heterogeneous catalysis, and how the catalysis is going to happen, that is explained based on this adsorption theory also. So what happens in the adsorption theory means, first point is diffusion of reactant to the surface of catalyst. So for example, let us say this is your catalyst. This is the catalyst. What are the things which will happen? The reactant molecules has to come and reach the surface, that is diffusion of reactants to the surface of catalyst. After they reaching the surface, they should absorption of reactant on the surface. After they get absorbed, they should react with each other, two reactants to form products. The products which are formed, they should dissolve, and they should again diffuse back so that the new molecules can come. So these are the 5 steps. Yes or no? What are those 5 steps? Desorption of diffusion of reactant molecules to reach the surface. Diffusion of reactant molecules to reach the surface of catalyst. Second one, the reactant molecules diffuse and reach the catalyst. After reaching the catalyst, they should get absorbed. Absorption of reactant molecules on the surface. Third one, reaction of reactant molecules to form products. Desorption of products Desorption of products. From the surface of catalyst. From the surface. And lastly, diffusion of products. Although they dissolve, if they are present near the surface only, the new reactant molecules cannot come. So diffusion of products away from surface. So all these steps are actually there, which are present in the adsorption theory of the respective catalysis. So reactant molecules reach, they form the products. The reaction is going to happen between the reactant molecules. Products are going to be formed. The products are again going to be dissolved, and they are again going to be diffused. Right? Is that point clear to everyone or not? All these 5 steps.
Yes, sir.
Yes, sir.
Yes.
Yes, right. So now we have catalysts in the industries also. In industries, what type of catalyst we have? General examples. Iron is used as a catalyst and molybdenum as promoter. It is used in the heterogeneous catalysis and Haber's process. Haber's process for the synthesis of ammonia. There you have iron as catalyst and molybdenum as promoter. Platinized asbestos. Ostwald's process for HNO3 from NH3. It is again heterogeneous catalysis. Ostwald's process for HNO3 from ammonia. That is also heterogeneous catalysis. V2O5, vanadium pentoxide, that you are going to use in which process? Contact process. We will have contact process for the preparation of H2SO4. There you have vanadium pentoxide, where heterogeneous catalysis is again used. Nickel as catalyst and copper as promoter for the hydrogenation of vegetable oil, or again heterogeneous catalysis. Hydrogenation of vegetable oils or heterogeneous catalysis is going to be there, where nickel is used as a catalyst and copper is used as a promoter. Is that clear or not?
Yes, sir.
Right. Shape selective catalysis by zeolites. Shape selective catalysis by zeolites. What are zeolites? Zeolites are shape selective catalyst. That means the catalytic action that depends upon the pore structure of the catalyst. The catalytic action, whatever we have, that will depend upon what? Pore structure. Like in the catalyst, we have a particular pore, and size of the reactant and product molecules. That is said to be shape selective catalysts. The catalytic reaction that depends upon the pore structure of the catalyst and the size of reactant and product molecules, that is called as shape selective catalysis. Shape selective catalyst. The pore size is generally in the range of 260 to 740 picometer. Whatever the catalyst we have, the pore size of that particular catalyst will be in the range of 260 to 740 picometer. Examples, zeolites, as I was saying, zeolites are shape selective catalysts. They are good shape selective catalysts because of their honeycomb-like structures. What are those? They are good shape selective catalysts because of their honeycomb-like structures. What are zeolites? Zeolites are aluminosilicates. Yes or no? Aluminosilicates. And how many types of silicates we have? Orthosilicate, pyrosilicate, 3D sheet silicates. Yes or no? Many silicates are there. In the silicate, which is the repeating unit?
SO2.
Silicates
SN.
have SiO4 4 minus as the basic unit. If two SiO4 4 minus units have been combined, you will get Si2O7 6 minus. Like based on the number of silicate units combined, you will be getting different other types of silicates. These zeolites are aluminosilicates and they are 3-dimensional silicates. They are 3D silicates. They are three-dimensional silicates, right? Zeolites, as I was saying, they are microporous aluminosilicates. They are 3D silicates. Zeolites, before using as catalyst, are heated in vacuum so that the water of hydration, whatever the water of hydration we have, that is going to be lost, and a resulting zeolite become porous. Because we should have a pore size. No, pore size is 260 to 714 picometer we said, but that pore size has to be free. If it is surrounded by water, the pore although is there, it is not available. So the pore sizes, to make the pores free from water, we will be heating them. As a result of heating, whatever the extra water we have, that water of hydration, that is going to be lost, and it becomes even more porous. Because of that porous nature, you can use this. And they are microporous aluminosilicates, means what you can understand, some of the silicon atoms have been replaced by aluminum in the silicates. Some of the silicon atoms were replaced by aluminum in a 3D structure. Some of the silicon atoms were replaced by aluminum in the 3D structure, and that is why the name aluminosilicates. Normally, zeolites are used in the petrochemical industries for cracking of hydrocarbon and isomerization. And we know that whatever the alcohol is going to be converting into gasoline in the presence of a zeolite known as ZSM5. Alcohols converting into petrol or gasoline in the presence of a zeolite known as ZSM5. Normal zeolites are used in the petrochemical industries for cracking of hydrocarbon and isomerization. Alcohols will be converting into respective gasoline or petrol in the presence of ZSM5. You have to remember this. That is, ZSM5 is a particular zeolite. Is everything clear, students, so far?
Yes, sir.
Yes, right.
Yes.
Enzyme catalysis. What are enzyme catalysis? We are using enzymes as catalysts. Enzymes as biocatalysts. Enzymes, we all know, they are actually catalyzing the biological reactions happening. They are actually catalyzing the biological reactions happening inside the human body. So enzymes are complex nitrogenous organic compounds which are produced from living plants and animals. They are actually protein molecules of high molecular mass, and they form what? They form colloidal solutions in water. If they are forming colloidal solutions in water, what type of category they belong to? Based on the type of dispersed phase particle, they will be called as what type of colloids? Based on the type of dispersed phase particle, we have three types of colloids: multimolecular, macromolecular, and associated. They belong to what type of category?
Macromolecular.
Yes, macromolecular colloids. Multimolecular colloids means whenever the crystalloids are combining with each other and forming a colloidal particle. Macromolecular colloid means the colloid particle itself is in the like a macromolecule, like a protein molecule or any enzyme. Associated means micelle formation. Next, they catalyze biochemical reactions, therefore also known as biochemical catalysts. Biochemical, they are also called as biochemical catalysts, and the phenomena is called as biochemical catalysis, or simply we can call them as biocatalysts. Simply we can call them as biocatalysts. And we have to remember different enzymes used for different types of reactions. Like if I try to convert sucrose to glucose and fructose, what type of enzyme you can use?
Sucrose.
Maltase. Maltose to glucose if I am doing.
Maltase.
Maltase.
Starch to maltose.
Zymase.
Zymase or diastase. Glucose to ethyl alcohol and carbon
Diastase.
dioxide. Yeah, glucose to ethyl alcohol and carbon dioxide. Zymase. Urea
Zymase.
to, yeah, urea to ammonia and CO2.
Urease.
Urease. And the proteins, they are converting into amino acids in the presence of enzyme known as pepsin as well. Okay, very good, all of you. So reactions catalyzed by enzymes. So different types of reaction and different types of enzymes. So these are the categories. These are the point to be remembered. Okay. We have to remember these points. You cannot say like why invertase is actually, you can ask a question, that is a valid question. Sucrose is converting into glucose and fructose. Why zymase, why invertase is catalyzing the reaction? Why not zymase? As I was saying, for a particular type of reaction, you will be having only one type of enzyme as a catalyst. Catalysts are highly specific and they have to react with the respective reactant molecules. The enzyme will be developing a new intermolecular force of attraction with the reactant molecules. The enzyme will hold the reactant molecules. It has to provide the functional groups for the reactant molecules so that the reaction can occur. Like we have discussed the same in chemistry in everyday life. What is the role of enzyme? The enzyme will be holding the reactant molecules. After holding the reactant molecules, it should provide the functional groups for the reactant molecules to react and form products. Okay. So these are the different types of enzymes and their sources and the type of reactions. If you think of characteristics of enzyme catalysis, the enzymes, they are highly efficient. One molecule of an enzyme may transform 1 million molecules of reactant per minute. Enzymes are highly efficient. One molecule of enzyme may transform 1 million molecules of reactant per minute. You can just look at this, how efficiently they are working. They are highly specific in nature. One catalyst cannot catalyze more than one reaction. If you take one catalyst cannot catalyze more than one reaction. That means for every biochemical reaction, we have a specific catalyst. For every biochemical reaction, we have a specific catalyst. They are highly active under optimum temperature. What is the optimum temperature for them? Like 298 Kelvin to 310 Kelvin. Some people again say, like whenever a foreign material like virus or bacteria enter the body, the immune system has increased the temperature of the body so that those foreign molecules will die. And you are taking a medicine to decrease the temperature. So why can't you be in high fever? So that because of that increased temperature, the foreign molecules can die. Because of increased temperature, the biological activity is going to be defected, because highly active under optimum temperature only. The enzymes are highly active under optimum temperatures only. And highly active under optimum pH, like 5 to 7 is the pH. Under that pH only, they are going to be highly active. Increasing activity in the presence of activators, like in the presence of normal catalyst we use in a chemical reaction. What do we call that? If you have a normal catalyst, promoters are those substances which increase the activity of the respective chemical reaction. If a substance increases the activity of a catalyst, it is said to be promoter. In the same way, enzymes are biocatalysts. Increasing activity in the presence of activators and coenzymes. Whenever we have activators and coenzymes, they are going to increase the activity of a respective enzyme. Okay. Similar to promoters, increasing activity in promoters, how they are increasing the activity of catalysts. Similarly, activators like Na+, Mn+2, CO plus 2, Cu plus 2, they will increase the activity of a respective biocatalyst known as enzymes. Is that clear or not?
Yes.
sir.
Yes or no? And mechanism of enzyme catalysis, like key lock theory. Like what this theory says is, enzyme will react with substrate to form a complex, enzyme substrate complex. And that enzyme substrate complex will be converting into enzyme and product is going to be released back. Enzyme plus substrate will be forming an enzyme substrate complex. This enzyme substrate complex is converting into products and enzyme is released back. These are the reactions. This is the first step. This is the second step. Enzyme plus substrate forms enzyme substrate complex, and this enzyme substrate complex is forming products. So rate of product formation or rate of reaction will be directly proportional to where the product is formed, in which reaction.
Second reaction.
Second reaction,
Second
let us say
reaction.
this is K2. First reaction, enzyme plus substrate forming enzyme substrate complex, and this will be maintained at equilibrium, and this is the slowest step. So rate of a reaction is directly proportional to concentration of enzyme substrate complex only. Why? Because the products are formed in the second reaction. Rate of reaction is directly proportional to concentration of enzyme substrate catalyst, enzyme substrate complex. So to eliminate the proportionality, I have to insert a constant. So rate R is equals to, what is the constant I have mentioned? K2. K2 into concentration of enzyme substrate complex. But enzyme substrate complex, is it an intermediate? Can we have intermediates in the rate expression?
No, sir.
We should not have we should not have intermediate in the rate expression. So how to eliminate the concentration of that intermediate?
From first reaction by
First reaction, yes. First reaction, we have to consider at equilibrium. At equilibrium, what is happening? At equilibrium, rate of forward is equals to rate of backward. Rate of forward equal to rate of backward means I can say K1 into concentration of enzyme into concentration of substrate is equals to K minus 1 into concentration of enzyme substrate complex. So concentration of enzyme substrate complex is equals to K1 by K minus 1 into concentration of enzyme into concentration of substrate. So you can substitute that here. So rate R is equals to K1 K2 divided by K minus 1 into concentration of enzyme into concentration of substrate. This is how you can understand the rate of reaction for this particular enzyme catalysts. Are you getting this logic or not?
Yes, sir.
Yes, sir.
Yes.
K1 K2 by K minus 1 into concentration of enzyme into concentration of substrate. That is how you can actually understand the rate of reaction for this enzyme catalysts. There are number of active centers of definite shape present on the surface of colloidal particles of enzymes. Do we really have the shapes?
No, sir.
Do we really? We do not have any shape. It is just like the electrostatic attraction or ionic attraction or hydrogen bonding or van der Waals bonding between the enzyme and the substrate. So active centers means the enzymes are going to attract the respective substrate molecules. They will attach molecules of reactant or substance which have complementary shape. That means whenever there's an attraction between enzyme and reactant, they will fit. That is like a key fits into a lock. Like a key is going to fit into a lock, like that the enzyme will hold the substrate. In the presence of active groups, an activated complex is formed, like enzyme substrate complex, which decomposes to yield the product, which decomposes to form the respective product. Is everything clear, students, so far?
Yes, sir.
Yes, sir.
Yes.
Yes or no? So this is nothing but your respective enzyme catalysts as well as catalysis. So this is surface chemistry where you have studied about adsorption, colloidal systems as well as catalysis, catalyst and catalysis. Just a second. So the next topic which we are going to start with is hydrogen. hydrogen and its compounds. So in this topic, we will be studying about hydrogen and compounds of hydrogen like water, hydrogen peroxide, as well as heavy water. Yes or no? So we also look at the preparations of hydrogen and different other properties also we'll be studying. So hydrogen is also used as a fuel, it is nothing but hydrogen economy. Yes or no? Hydrogen is also used as a fuel, which we call it as hydrogen economy. So let us start with this. Introduction. It is the lightest element and lightest gas in the periodic table. It is the lightest element and lightest gas in the periodic table. And the position of hydrogen is still not known. Its position is not fixed till now, since its properties match both with the group 1 as well as group 17. Thus, it can be placed in first as well as 17th group. And that is why it is separately placed in the center of the periodic table. Its nucleus has one proton, but does not contain any neutron. Its nucleus has one proton, but it will not have any neutrons. It has three isotopes, namely protium, deuterium, and tritium. Protium H11, that will have how many number of neutrons?
0.
0. Deuterium H12,
1.
1. Tritium H13, it will have respective 2. So number of neutrons are going to be changed. And which bond? Because of the increase in the number of neutrons, bond strength is going to be affected. If you think of organic chemistry, there also we have discussed CT bond, CD bond, and CH bond. Which bond is stronger bond?
CT bond.
CT bond. How we have explained that concept based on the concept of reduced mass. Protium is the main isotope having 99.9% abundance, and the remaining all, like the deuterium and the tritium, they have very less abundance. Methods of preparation. The metals which are placed above hydrogen in the electrochemical series on reaction with acid, base, and water give H2. Like if you take a particular metal M, which was in the +2 stage, and M +2 will take up 2 electrons to form a metal M. And we have hydrogen. This is nothing but the reduction potential SRP value. And we have hydrogen 2H plus will take up 2 electrons to form H2 gas. If you can try to write the combined reaction of these two, I can write metal converting into M +2 plus 2 electrons, 2H plus 2 electrons forming respect to H2 gas, 2H plus 2 electron forming respect to H2 gas. When I try to add these equations here, if it is SRP is -X. For hydrogen, what is SRP? 0.
0.
For M to M plus 2 electrons, what is -X becomes +X or not?
Yes,
It is again 0. So metal, the complete reaction is metal is taking up 2 H plus ions, that is H plus ions are there in the acidic solution, forming M plus 2 and H2 gas is evolved. For this reaction, what is E0? E of cell.
Positive.
E of cell
Plus
is equals to E0 of cell is equals to E0 of M2 M plus 2 plus E0 of H plus 2 H2. E0 of M2 M plus 2 is how much?
+X.
Plus X plus E0 of H plus 2 H2 is 0. That means plus X. Ultimately, you have E0 of cell as plus X. So delta G0 is equals to minus NF E0. E0 is positive. So therefore, delta G0 is less than 0. Since E0 is greater than 0, delta G0 will be less than 0. Therefore, cell is spontaneous. The cell reactions are going to be spontaneous since delta G0 is going to be negative. Is that clear or not?
Yes.
yes, sir.
These are actually the methods of preparation of respect to H2 gas. Since the electrochemical series have been arranged in the increasing order of standard reaction potential value, since M plus 2 electron gives us to M is -X and H plus 2 electron gives us to H2 is 0, can I say a metal M is actually placed above the hydrogen in the electrochemical series?
Yes, sir.
The
Yes.
metals
Yes.
which are above the hydrogen in the electrochemical series will have a net electrode potential for the cell to be positive. So delta G naught is negative. Since delta G naught is negative, so that reaction is going to be spontaneous, right? Metals which are placed above hydrogen in electrochemical series on reaction with acid, base and water gives H2 since delta G naught is negative. So zinc impure plus dilute H2SO4 gives ZnSO4 plus H2. Iron plus dilute H2SO4 gives FeSO4 plus H2. Iron plus dilute H2SO4 will be giving FeSO4 plus H2. These are the type of reactions which produce H2 gas. From base, only amphoteric metals like beryllium, aluminium, zinc, tin, lead gives H2 on reaction with NaOH. You have to remember these metals. Only amphoteric metals, like in the previous step, we have said that metals which are placed above hydrogen react with acid, base, and water. They give H2. Yes or no? Metals which react above hydrogen electrochemical series, they react with acids, base, and water. With acids, metals are reacting to form H2. With the bases, what type of metals react? Although they are above hydrogen, only amphoteric metals will react, like beryllium, aluminium, zinc, tin, and lead. Beryllium, aluminium, zinc, tin, lead, they will react with the base to form H2 gas. Zn plus 2NaOH gives us to Na2ZnO2 plus H2. Sodium zincate. Aluminium plus NaOH plus water forms respective sodium metaluminate NaAlO2 plus H2. Similarly, beryllium can also react with NaOH to form sodium berylate Na2BeO2. Beryllium plus NaOH forms sodium berylate plus H2. So amphoteric metals, they will react with the respective NaOH to form H2 gas. Along with the H2 gas, sodium zincate, sodium metaluminate, sodium berylate has been formed. Is that clear, students?
Yes, sir.
Metals react with acids to form H2 gas, which are above hydrogen. Above hydrogen, whatever the metals we have, which are amphoteric metals, they will react with the respective bases. With the water also the reaction will occur, like with the cold water, with hot water, how the reactions happen, we'll see now. From water, what you can say? With the cold water, there are some specific metals which are going to be reactive. With hot water, different metals. With the steam also, we have different metals. Lesser reactive metals we have, like iron to tin, they are going to be reactive with steam only, and they form H2 gas. With the hot water, reactive metals like aluminium to chromium, they will be reacting to form respective H2 gas on reacting with hot water. With the cold water also, we have highly reactive metals like 1A and 2A metals. Except lithium, beryllium, and magnesium, 1A and 2A metals, they will react to form respective H2 gas. To form respective H2 gas, 1A and 2A will be reacting. Right? So these are the reactions where metals react with acid, base, and water to form H2 gas. Which metals react with the base? Amphoteric metals. Which metal react with the water? Like cold water, highly reactive, hot water, reactive, with the steam, less reactive metals. Right? Commercial method is the electrolysis of acidified water. Water you take, water is a weak electrolyte which dissociates to produce H plus and OH minus ion. Water is a weak electrolyte which dissociates to produce H plus and OH minus. And if you try to add a trace of acid or base, this H plus and OH minus ion concentration is great. So at anode is positively charged. So negatively charged OH minus comes. 2 OH minus will be reaching the anode to form H2O and nascent oxygen and 2 electrons. Whenever we have 4 OH minus, 4 OH minus will form 2 H2O. Along with that, O2 gas is obtained and 4 electrons are obtained. O2 gas is obtained at anode. At cathode, what obtained? Cathode is negatively charged. So positively charged H plus ions 2H plus will take up 2 electron to form the H2 gas. 2H plus will be reacting with 2 electron to form H2 gas. This was the reaction happening at cathode, and the other reaction is happening at the anode. Electrolysis of acidified water will form respect to H2 gas at the cathode and O2 gas at the anode. You do the electrolysis, you are getting O2 gas at anode and H2 gas at cathode. Is that clear or not?
Yes,
Yes,
sir.
sir.
Next one, commercial method from hydrocarbon. CnH2n plus 2 plus NH2O upon heating in the presence of nickel at a very high temperature forms a CO and 3n plus 1 types of H2. Like if you look, write the balanced equation, you are getting CnH2n plus 2 plus NH2O is forming NCO and 3n plus 1 H2. Reaction of steam on hydrocarbon or coke at high temperatures in the presence of catalyst forms H2 gas. You can write down the reaction. Reaction of steam on hydrocarbon or coke at a high temperature in presence of catalyst forms H2 gas, and the mixture of CO and H2, that is called as what?
Water gas.
The mixture of CO plus H2 is called water gas. This mixture is used for the purification of different kinds of hydrocarbons. This mixture is used for the purification of different kinds of hydrocarbons, and that is why it is called as synthesis gas or syngas. And that is why it is called as synthesis gas or syngas. Okay, and as I have told you, we have seen the reaction of hydrocarbon with water in the presence of a catalyst at very high temperature. We can also do the reaction of coke, like C plus H2O, carbon solid plus H2O gas will be forming respective CO gas and H2 gas. This reaction is also called as coal gasification. The process of converting or producing syngas from coal. The process of producing syngas from coal is also called as coal gasification, because you are trying to convert the coal into respective CO and H2. CO and H2 both are gases. Okay.
Yes, sir.
Yes. So the hydrocarbons can be heated in the presence of steam, or the coke can also be heated in the presence of steam, getting CO and H2. Coal gasification is converting of coke to H2, CO and H2. CO and H2 is used for the synthesis of many organic compounds. That is why last class we have seen that enzymes CO plus H2 used to produce CH4 or CHCOH. Many hydrocarbons or derivatives are produced. That is why it is called as synthesis gas or syngas. Bosch process is from water gas shift reaction using iron chromate as catalyst. What is water gas shift reaction? The CO, okay, CO plus H2O is going to be converted to CO2 and H2. Understand this. This reaction is nothing but water gas is called as water gas shift reaction, where the water gas, whatever you have, right, that CO is obtained from water gas. CO is obtained from water gas or syngas or synthesis gas. That CO obtained from water gas or syngas, that is treated with steam at high temperature, 673 Kelvin, forming CO2 and H2. That means the water gas has been again converted to H2 in the presence of catalyst like iron chromate. What is that iron chromate? Fe2 CrO4 taken thrice. That is, we have 3 CrO4 2 minus and 2 Fe plus 3. And this reaction is, this is nothing but water gas shift reaction. Water gas shift reaction is this reaction. C plus H2O converting into CO and H2. This is called as what? That is called as coal gasification. C plus H2O converting into CO plus H2. That is called as coal gasification. This reaction is called as coal gasification, and the mixture of CO and H2 is called as water gas or syngas. CO plus H2 in the right. So these are the different ways of preparing H2 gas. The compounds of hydrogen like hydrides, ionic hydrides, covalent hydrides, interstitial hydrides will start in the next class. Fine. Thank you all, everyone. Bye.
Thank you, sir.
Thank
Thank
you.
you, sir.